Welcome to Thermodynamics Lecture series. In the previous video, we discussed the work transfer. In the present video, we are going to discuss about the heat energy transfer. First, we will discuss the definition of the heat. Heat is a form of energy transferred across a boundary due to a temperature difference. The temperature difference acts as the driving potential, while heat transfer represents the resulting flux. So due to the temperature difference, heat energy will transfer across the boundary, and temperature difference is a driving potential for heat transfer between the system and surrounding. Heat transfer can occur through the following three primary mechanisms. First one is the conduction. Conduction is the transfer of heat between two bodies in a direct physical contact. And the second one is the radiation. Radiation is the transfer of heat between bodies separated by empty space or a medium achieved through the electromagnetic waves. So third type of the heat transfer is convection. Convection refers to the transfer of heat between a solid surface and a moving fluid. So this is the schematic representation of the direction of heat transfer. Heat flow into a system is taken to be positive, and heat flow out of a system is taken as the negative. Next, we will discuss the adiabatic process, a process in which no heat crosses the boundary of the system is called an adiabatic process. Adiabatic process is one in which there is only work interaction between the system and its surroundings. So in the adiabatic process, only work interaction occurs between the system and surroundings, and therefore there is the no heat transfer occurs in the adiabatic process. And the unit of the heat is joule in the SI units. Heat transfer is a path function similar to a work transfer, which means heat transfer tells how energy was transferred, not how much energy is transferred in a system. So heat transfer value changes depending on the process path, unlike the state function like temperature or internal energy. Therefore, dq is an inexact differential, and we are representing integration of 1 to 2 dq equal to the q12. So next we will prove that heat is the path function with one example. Let's consider two different paths with same initial and final state. First one is the constant volume path. Second one is the constant process path. So first we have to see the constant volume path, that is the isochoric path. We know that when in the constant volume process, work done is the 0. Then, so net heat is the equal to the internal energy, which is equal to the NCV T2 minus T1. Next, we have to look for the amount of the heat in the isobaric path or constant pressure path. And we know that when the constant pressure path, work equal to the integration of PdV, which is equal to the nR T2 minus T1. Then heat equal to the internal energy plus work done. Then net amount of the heat in the constant pressure path is NCP T2 minus T1. So here we have to observe that when the different path between the same end state gives the different heat transfer. So heat depends on the path only. Next we will discuss the specific heat. Specific heat of a substance is defined as the amount of heat required to rise a unit mass of the substance through a unit rising temperature. The symbol of the specific heat is small c, and small c specific heat equal to the Q divided by M into delta T, and units of the specific heat is joule per kg Kelvin. Here Q is the amount of heat transfer and small m is the mass of the substance and delta T is the rise in temperature. So next we have to discuss this specific heat with one example. So let's consider we have to heat the 500 grams of water from 20 degrees centigrade to 30 degrees centigrade. Here M is given that one the 0.5 kg, and we know that one the specific heat of water equal to the 4186 joule per kg degree Celsius. And here temperature rise is the 10 degrees centigrade, that is the from 20 degrees centigrade to 30 degrees centigrade, then delta T equal to 30 minus 20, which is equal to the 10 degrees centigrade. Then amount of the heat which is equal to the Q equal to MC delta T. Here we know the M value and C value and delta value. Then Q value is the 20,930 joules. So here 20,930 joules of heat energy is required to raise the temperature of 0.5 kg of water by 10 degrees Celsius. And the product of mass and specific heat, that is M into C, is called as the heat capacity of the substance, and we are representing the capital letter C. So capital letter C is the heat capacity which is equal to the MC. So next we have to see the latent heat. Latent heat is the amount of heat transfer required to cause a phase change in unit mass of a substance at a constant pressure and temperature. There are three phases in which matter can exist, that is solid, liquid and vapor or gas. Then the latent heat of fusion is the amount of heat transfer to melt unit mass of solid into liquid or to freeze unit mass of liquid to solid. So latent heat of fusion is amount of heat transfer between the solid and liquid or maybe liquid to solid. So next we have to look for the latent heat of vaporization. So latent heat of vaporization is the quantity of heat required to vaporize unit mass of liquid into vapor or condense unit mass of vapor into liquid. So next we have to look for the latent heat of sublimation. So latent heat of sublimation is the amount of heat transferred to convert unit mass of solid to vapor or vice versa. Next we will discuss the one example problem in the heat energy transfer. So let's see the problem. It is required to melt 5 tons per hour of iron from a charge at 15 degrees Celsius to molten metal at 1650 degrees Celsius. The melting point is 1535 degrees Celsius and latent heat is 270 kilojoule per kg. Specific heat in solid state is 0.502 kilojoule per kg Kelvin, and in liquid state 29.93 divided by atomic weight kilojoule per kg Kelvin. If an electric furnace has 70% efficiency, then find the kilowatts rating is needed. Similarly, if the density in molten state is 6900 kg per meter cube and the bath volume is 3 times the hourly melting rate, find the dimensions of the cylindrical furnace if the length to diameter ratio is 2 and also given the atomic weight of iron is 56. Let's see the solution. So here I have to determine the rate of heat supplied. So before that one, first we have to determine the heat required to melt 1 kg of iron at 15 degrees Celsius to molten metal at 1650 degrees Celsius. Then heat required to melt 1 kg of iron at 15 degrees Celsius to molten metal at 1650 degrees Celsius equal to energy to heat solid iron plus energy to melt the iron plus energy to heat the molten iron. So in the three phases we have to determine the heat required. So first we have to look for the energy is required to heat the for the solid iron. So that is the heat required to rise the temperature from the charge temperature is at the 15 degrees Celsius to melting point, that is the 1535 degrees Celsius, plus latent heat plus heat required to rise the temperature from 1535 degrees Celsius to 1650 degrees Celsius. So which is equal to the, we know that one, heat equal to the mass into specific heat into temperature change. Similarly, we have to calculate the heat in the solid and also latent heat, and also similarly liquid to up to the 1650, that is the mass into specific heat into temperature change. So up to the from the solid to up to the liquid, and latent heat into mass in the liquid phase, solid to liquid phase, and next specific heat in liquid state into mass into temperature change from the melting point to liquid temperature. Then this can be written as, so mass is given, here we are considering the heat required to melt the 1 kg of iron, so mass is the 1 kg, then 1 into specific heat for the solid state is given 0.502 into temperature change. So charge is at 15 degrees centigrade in the solid and melting point is the 1535 degrees Celsius. Then temperature is the 1535 minus 15 plus, and the latent heat into mass. So latent heat is given 270, mass is the 1 kg. Similarly, specific heat in liquid state is given 29.93 divided by atomic weight, that is the 56. So specific heat is the 29.93 divided by 56. Mass is the 1 kg and temperature change is the, molten liquid metal is temperature at 1650 minus melting point, that is the 1535. So 1650 minus 1535. So net amount of heat required to melt the 1 kg of iron at 15 degrees Celsius to molten metal at 1650 degrees Celsius equal to the 763 plus 270 plus 61.5, which is equal to the 1094.5 kilojoule per kg. But here we have to calculate the heat required to melt the 5 tons per hour. So which is equal to the melting rate is 5 tons is 5 into 1000 kg per hour. So the rate of heat supply required is the 5000 into 1094.5. So next we have to calculate the, if the furnace efficiency has the only 70%, then rating of the furnace would be rate of heat supply per second divided by furnace efficiency. So here rate of heat supply, so per hour equal to the 5000 into 1094.5. So then I have to convert the seconds mean divided by 3600, and furnace efficiency is the 0.7. So rating of the furnace is the 5000 into 1094.5 divided by 0.7 into 3600. Then its value is the 217 into 10 to the power 3 kilowatts. Next we calculate the dimensions of the cylindrical furnace. Here it is given the density in molten state is 6900 kg per meter cube, and we know density equal to the m by v. And in the data it is mentioned that one bath volume is 3 times the hourly melting rate. So then mass equal to the 3 into 5000 kg. Here substitute. So in the density formula, we will get the volume. So here we know the mass, that is the 3 into 5000. Density value is 6900. Then 15,000 divided by 6900 equal to the 2.18. So volume equal to 2.18 meter cube. And here it is mentioned the geometry of the furnace is cylindrical furnace, and also mentioned that when the length to diameter ratio is the 2. Let's consider diameter is the small d and length is the small l. Then L equal to the 2d, and we know volume is the, for the cylindrical furnace, pi by 4 d square into L, which is equal to the 2.18. Then here it is given the L equal to the 2d. Then substitute L equal to 2d here. Then d value is the 1.15 meters. Then the L become the 2.3 meter. So this is the solution, and thank you.